Hi everybody, welcome to another video on Calculus 1, section 4.7, the Habitual Rule. If you type it and you cannot type the head, it can be in this form. Yeah, which is still the same thing. Alright, so before we start the section, I just review the indeterminate forms. What we have up to this point is 0 over 0 and infinity over infinity. Those are indeterminate form. So let me write this. So 0 over 0 and infinity over infinity. Of course, could be plus or minus. These two are indeterminate. Right. Now, of course, there will be a few more, but those are the two that we'll focus on now. And let's see something that is not indeterminate, that we also important, that we need to know those. If we have 0 divided by something that is not 0, it will be 0. And if we have something not 0 divided by 0, it is undefined. But it could go to infinity or negative infinity. If it is one-sided limit, it could go to infinity. But for now, I just write this as does not exist. If there's a one-sided limit, they may or may not exist. So in this case, once again, even infinity, we could say that does not exist. It could be infinity. Right. Now the other form, if we have infinity divided by something that it is finite, of course finite is opposite to. By opposite I mean that is not infinity. Of course that could be plus or minus. Plus or minus. And then if we have finite divided by something that goes to plus or minus infinity, that equal to 0. Right. And those are not indeterminate. Those two are. But there will be a few more. Right, first, the Orbital Rule theorem. Now we focus on the case of 0 over 0. Now, suppose the function f and g are differentiable on an interval containing the point where x approaches to where we find the limit. Denominator is not equal to 0 because divided by 0 is undefined. The limit could be infinity, negative infinity, or does not exist. Now if the limit, the top goes to 0, the limit of the bottom goes to 0, then the limit of the quotient is the limit of the quotient of the derivative. So most important things here, this is not quotient rule. We take derivative of the top, derivative of the bottom, the limit will be equal to. They are not equal to, but the limit will be equal to. And provided that the limit on the right side exists, or could be plus or minus infinity. And of course this also works for one-sided limit. But the focus here, of course, the note. First of the note, this is not a quotient rule. And second, it only applies to indeterminate form. I just write abbreviate that for indeterminate form. If it is not in the indeterminate form, do not use the Habitual Rule. That's what I mean here. Right. Let's have a look at the first example. Right. Now the first thing when we're trying to find limit, of course we put in the numbers. See what happens. If we put 1 in here, 1 cubed plus 1 square minus 2 times 1 over 1 minus 1. Notice that I do not write the equal sign here right away. Just put in the number first. See what happens. 1 plus 1 minus 2 on the top is 0. 1 minus 1 is 0. So we have 0 over 0, which is the indeterminate form. So in that case, we can use the Habitual Rule. Only when it is in indeterminate form, we can use the Habitual Rule. Right. So we check the limit. Now the Habitual Rule says we check the derivative of the top and then the derivative of the bottom. The derivative of the top is 3x squared plus 2x minus 2. The derivative of x minus 1 at the bottom is 1. Of course, when we divide by 1, we don't need to write like that. We just say 3x squared plus 2x minus 2. And this will be easy now. We'll just put 1 in because this is a polynomial. It's guaranteed to exist. So put 1 in here, we have. Now this I'm sure is going to be equal to because polynomial defined and continuous everywhere. So we have 3 plus 2 minus 2, so the answer is 3. Alright, of course, if we did this back in the first part of the book, when we don't know the derivative, we have to do the factor, and then they should have common factor to cancel. That certainly works, but this will be a lot better. We use the Hablo Rule. If it is in indeterminate form, that will be take the derivative of the top, divide by the derivative of the bottom. So that will be very simple compared to the other way. Now, let's look at this example. Because the first thing I do, put in the number, see what happens. Don't write the equal sign yet, because it might turn out to be something nice. So we do that. 2 minus 2 on the top is 0. At the bottom, square root of 2 minus square root of 2, so we have 0 minus 2. Well, that is 0 divided by negative 2. 0 divided by anything else other than 0 is going to be 0. So since that is not indeterminate form and this is 0, we can just make it equal to, and that's what the limit is. Right. So don't use the Orbital Rule if it is not indeterminate form. Right. Next, let's look at this one. Sine of x over x. If we put in 0, we have sine of 0 over 0. By the way, in section 3.5, there's a theorem saying limit as x equal to 0 of sine x over x is equal to 1. And we use trigonometry and the Swiss theorem and a lot of other things to prove it. Here, first thing, of course, always put in 0. Put in the limit. It just happened to be 0 over 0. And 0 over 0 is one of the indeterminate form. That means we can use the Habitual Rule. So take derivative of the tops, derivative of sine, cosine, derivative of x is 1. Or this is just cosine. Then we'll put in 0. Once again, similar to polynomial, sine, cosine are defined and continuous everywhere. So I know for sure that if I put in any number here, it will define. Cosine of 0 is equal to 1. And this is of course a lot easier to prove than using geometry, trigonometry, sway theorem, and a lot of things that we did in section 3.5. Again, just have that. Right. Next, let's look at this one. Secant of x minus 1 divided by x squared. Now, of course, first thing, always put in the numbers. See what happens. Secant of 0 minus 1 over 0 squared. Secant of 0 is 1 over cosine of 0 minus 1 over 0. Now, we did have cosine of 0 is equal to 1. So 1 minus 1 is 0 over 0. So that's good. This is, 0 over 0. So this is indeterminate form. And we can use the Hablo Rule here. So checking derivative of the top, derivative of secant is secant tangent, right? And derivative of x squared is 2x. Right. Now, if we put in 0, let's do that again. Put in 0. Secant of 0, which we have, is 1. And tangent of 0 over 2 times 0. Now secant of 0 is 1. Tangent of 0. Tangent of 0 is sine of 0 over cosine of 0. So we have sine of 0 is 0. Right? So we just have 0 over 0 again. So what do we do after that? Of course, if it is indeterminate, we can continue using the Hablo Rule. And in this case, I will do that. Right. Derivative of the bottom is easy, it's 2. Now derivative of the top, this will be a product rule. So derivative of the first will be secant tangent times the second minus secant times the derivative of the second. Derivative of tangent is secant squared. Right, now let's simplify this. That gives us secant tangent square minus secant cube over 2. Now, since we divide by 2, we know that this one exists. Unless of course the secant and tangent does not exist. Now let's put in 0 and see what happens. The bottom is 2, which is good. So once again, put in the numbers, see what happened. So it's always like that. If it is in indeterminate form, we still continue and use the orbital rule. Of course, there's another way to do that, but I want to use the orbital rule here. So I put in 0. Over 2. Now, secant of 0 is 1. Tangent of 0 is 0. So this one we have negative secant cube of 0 divided by 2. And that equal to negative 1/2. Sorry, this is the product rule, so this will be a plus. Right? U prime V plus UV prime. Sorry. And secant cube of 0 is 1. So we just have 1 over 2. Or this is equal to 1/2. And a well-defined number. So we make the limit equal to. Right? So this problem, we use the orbital rule twice. Because 2 times we have the indeterminate form. Every time we have indeterminate form, we can use the orbital rule. And that's what we have. Right. I will do this in a different way. Now let's focus on this step here. I mean, that step. Right. Section 3.5. Limit of sin x over x when x goes to 0 is equal to 1. And limit of tangent x over x when x goes to 0 is also equal to 1. So in that case, I will split this into limits. One of which is secant x over 2. And the other one is limit of tangent over x. In section 3.5, or we can use the orbital rule again. This can be shown that equal to 1. And we put 0 in here, we have 1/2. So 1/2 times 1 is 1/2. Yeah, so if we don't want to use the orbital rule, we can also do that. But just so that we can use the orbital rule more than one time. As long as it is indeterminate form, we can use the orbital rule. Right, so that's what we have. Now, the next theorem we have is indeterminate form of infinity over infinity. And by infinity, I mean it could be positive or negative infinity. Still the same. If the top goes to infinity, the bottom goes to infinity, we can just use the orbital rule. Meaning, we take derivative of the top divided by derivative of the bottom. Once again, this is not the quotient rule. Derivative of the top divided by derivative of the bottom. Of course, that is the limit. In general, they are not equal to, but the limit will be equal to. Right, let's look at this example. Right, now, first, of course, we put in infinity. And of course, when we put in infinity, obviously, it's going to be infinity over infinity, right? So in which case, we can use the Hablo rule. Taking derivative of the top. (3x squared plus 2x). Derivative of the bottom, 6x squared minus 1. Right, and put in it put in infinity, we still have infinity over infinity. So keep using the Habitual Rule. And we have derivative of the top give us 6x plus 2, derivative at the bottom 12x. Put in infinity one more time, still infinity over infinity, so take derivative, use the Hablo rule one more time. Derivative of 6x plus 2, that's just 6 over 12, and that reduced to 1/2, and that is a nice number. By nice I mean defined, so I make it equal to, so we can use the Hablo rule repeatedly. As long as it is in indeterminate form, we can use the Habitual Rule, and indeterminate form could be 0 over 0, infinity over infinity. Now remember, we did use differently, we did do this kind of problem differently, right? So back in chapter 2, when we do this, and I say when we have this, we're just going to take the highest power term on the top and the highest power term at the bottom, right? So that just x cubed over 2x cubed. Yeah. So highest power term on the top, highest power term at the bottom. That's what we have. And then cancel the x cubed. This equal to 1/2. So that certainly works, and that should still work here. So as x go to positive or negative infinity, the highest power term matters. The other two is going to be less than that, so it's insignificant. So let me just write this. As x goes to positive or negative infinity, when we have a polynomial like this, only the highest power term matters. Right. So in that case, we can pick the highest power term and the highest power term tomorrow. Not only that, we might have, even though it is not polynomial, we still take the highest power term, because sine x is less than, between -1 and 1, so x cubed is a lot bigger than that, so that means sine x is negligible, so we just throw that away. It doesn't contribute to the limit. Yeah. Right. Now let's look at this one. Now when x go to pi over 2, tangent of, let's look at, put this in the calculator, radian mode, okay. Tangent of pi over 2. Which is good. Is this in radian mode? I'm sorry, tangent of pi over 2. Yeah, that's undefined, right? Now this go to from the negative side, from the left side. So what we do is we will do that, but we subtract a small number to it, right? So this guarantee, this show that the numbers will be a little bit on the left of pi over 2, and we have a very big number, so that means this tend to infinity, right? Same thing, secant is 1 over cosine. If we have pi over 2 going from the left, and we subtract a very small number, and also have a very big number. So when x goes to pi over 2, both the top and bottom goes to infinity. So let me write this. 1 plus tangent of pi over 2 from the left, secant pi over 2 from the left. The negative should be inside the parentheses. So, right, when we do that, we have infinity over infinity, which means we can use the Habitual Rule. Limit x goes to pi over 2. Yeah, when the number bisect we can write like that, but when there's a secant, it's better to put the minus in the parentheses. Right. Now, 1 plus tangent on the top, take the derivative of that. The derivative of tangent is secant tangent. I mean secant square. The derivative of secant is secant tangent. Right, of course we can cancel one of the secant. Cancel the secant. Which one of the secant on the top we have? Secant on the top, tangent x at the bottom. Now, that's good and all. What can we simplify this? Of course, we can still put in the numbers and see if it is equal to anything, but that doesn't help. I try something else, because if we keep taking derivative, and that once again secant tangent and then secant square, and that just cancel out. Let's try something else. Secant is 1 over cosine, right? And tangent is sine over cosine. So conveniently, if we multiply top and bottom by cosine, that cancel. We just have 1 on the top. One on the top. Cosine cancel, sine at the bottom. Now you put pi over 2 in it. 1 over sine of pi over 2. Sine pi over 2 is 1. From the left, still 1. So we have 1 over 1, which is 1. Yeah. So if we keep using the Hablo rule, it doesn't look like it could be something nice. Can simplify. I mean, we have secant tangent on the top and secant square at the bottom. We can cancel, and we still have a secant and a tangent. Right. Having said that, can we use this from the beginning though? So let's try it. Let's look at this from the beginning. Alright, that certainly works. Now let me do this differently. I will look at the original problem. The tangent, I will write sine over cosine. Secant 1 over cosine. So let's say if I don't want to use the Hablo rule, I just want to multiply top and bottom by cosine first. And multiply that in. Cosine times 1. Cosine cancel. Cosine cancel. We just have that. And then we put pi over 2 in. Cosine pi over 2 is 0. Sine of pi over 2 is 1. And you say, isn't that simply a lot better than this? And of course, yes. So what we see here is the Hablo rule is just a tool. I mean, sometimes it's to simplify the problem. Sometimes we just do this, get the same answer. didn't even have to do any derivative or the Hablo rule, just basic trigonometric identities. Of course, if you can do this, even better. Right? So the Hablo rule is give us a way to do it, but of course sometimes there might be a better way, like this, or of course that. But as long as it is indeterminate form, we can use the Hablo rule. That's for sure. Right. Talking about indeterminate form, they might be in different form. In this example, we have the indeterminate form of 0 times infinity. But as always, when we try to find a limit, first thing we do, put in the numbers, see what happened. So we have infinity square and then sine of 1 over 4 times infinity. Now, 1 over 4 times infinity. This one, we have a finite, let's spell it correctly, finite divided by infinity, which is 0. So in this case, we have infinity times sine of 0. Sine of 0 is 0. So 0 times infinity, 0 times any finite number, this is not 0, is infinity. Well, 0 times a finite number is 0. Infinity times something other than 0 is infinity. So in this case, this is also indeterminate form, which means we can use the Hablo rule. The only thing about the Hablo rule is that it has to be in the quotient. Not quotient rule, but it has to be a ratio of two functions. Here we have a product. So in order to use the Hablo rule, we need a ratio of two functions. So let me write that little note. So we need ratio of two functions. For using the Hablo rule. So I will rewrite the problem first before I go ahead and use the Hablo rule. Notice that in the problem, if I use the Hablo rule, I will denote that we use the Hablo rule. If we don't use the Hablo rule, I will just write equal to. So that's what distinguish between when we use the Hablo rule. Right. So what we can do here, we need a ratio, right? That means something has to go to the bottom. And x squared, if we move to the bottom, x squared move to the bottom, it becomes x to negative 2. Focus on the x squared here, move to the bottom, becomes x to negative 2. Cross the line, change the sign. Right, sign. Once again, x squared at the bottom, move to the top, cross the line, change the sign. Alright, let's rewrite this. Yes. On the top we have sine of 1/4 x to negative 2. The bottom is x to negative 2. Now we have a ratio of two functions. We can use the Hablo rule. Right. Right. Meaning we take the derivative of the top, derivative of the bottom. Take the derivative of the top, sine of something. It doesn't matter what inside of that. Sine, derivative is going to be cosine. And then derivative of the parentheses. At the bottom, derivative of this is -2 x to -3. Right, 1/4 x to -2, and then x to -1/4 x to -2. Right, we still have derivative here, don't forget that. So we have cosine 1/4 x to -2. Derivative of this, take down the -2 times 1/4 is -1/2. Right? -1/2. X to -3. And this is -2 x to -3. Cancel out x to -3 because all of them are just multiplied to this raised to the first power, right? So we can simplify. We cannot multiply into here because the 1/4 x to -2 belongs to the cosine. We cannot mess with that. This one to the first power, we can just go ahead and simplify the x to -3. And now -1/2 divided by -2. -1/2 divided by -2. That's just 1/4. Right? So -1/2 divided by -2 is 1/4. So we have limit x goes to infinity -1/2 divided by -2, that's 1/4. And then we just have the cosine of 1/4 x to -2. Now 1/4 x to -2, we can move that to the bottom. Once again, cross the line, change the sign. Yeah. The reason I move this to the top is that we can take derivative easier using the power rule here. Yeah. When we're done with that, we put that back to the bottom. Now, we did say that 1/4 over infinity, that is finite over infinity, so this one goes to 0 because this one goes to 0 because of finite divided by infinity. So bottom line is we have 1/4 times cosine of 0. Cosine of 0 is 1. So the answer is 1/4. By the way, I haven't this one x go to infinity, so we have infinity times 0. Yeah. So this one, if it go to infinity, we cannot actually graph it to see it. But if it is not infinity, we certainly can graph them. Let's just want to do one of them quickly. How about this one? Just want to at least graph one of them. Right, function secant, which is 1 over cosine. So that is, yeah, that is the top divided by x squared. Graph. As you see, when x go to 0, it is equal to 1/2. Yeah. Of course, if it does not go to infinity or negative infinity, then we can do that. But Yeah, let's just graph this one. X squared sine okay. I don't know what happened there, but strange. Zoom 6. Yeah, it looks like when x go to infinity, that's just flat. The limit when x go to infinity is 1/4. We have a horizontal asymptote. Look like that's what we have. Right, now, more indeterminate form. Indeterminate form of infinity minus infinity. Once again, if it is indeterminate form, we can use the Hablo Rule. Now, first, this one have to be a little bit careful here. Right, put in infinity, see what happened. Infinity minus infinity square minus 3 times infinity. Notice that infinity square minus 3 times infinity, those two, the x square has the higher power, so x square matters. The 3x doesn't matter when x go to infinity. So we don't really even have that, because x square has the higher power than the 3x. So that gives us infinity minus infinity. Regardless, indeterminate. Right, so that's good and all. Once again, if it is indeterminate, we can use the Hablo Rule. However, if we use the Hablo Rule, we should have the ratio of two functions, right? Which we don't have here. And that is subtract. We cannot move anything top and bottom. If it is multiply or divide, like the last example, it is multiply, we can move things top and bottom easily. But this is subtract, cannot do that. So we have to try something else. So once again, we need ratio of two functions. For the Hablo Rule. So it's not the Hablo Rule yet, but we need to have a ratio of two functions. And one little trick that we see back in the first chapter is when we have the square root, if we want to get rid of that or try to simplify things, usually we multiply by the conjugate, right? So that's exactly what we do here. Because the conjugate. Right, so multiply now the top, keep the bottom. Just need a ruler. Because this one is the conjugate to that. Right, so x times x, x times square root minus x times the square root and square root times the square root which yeah, give it a square root square. At the bottom, x plus x squared minus 3x. Alright, let's try to simplify this. X squared, middle terms cancel out. That's why we multiply by the conjugate. Square and undo the square root. Still have the parentheses now. At the bottom we have x because the x squared can cancel out. Let's say x squared minus x squared plus 3x. Right? The bottom is x plus x squared minus 3x. The x squared cancel out. I'll write that in the next line. That will be 3x x plus x squared minus 3x. Right. You may ask, why do we have to keep the x squared minus 3x here? Why don't we just keep the x squared? Because x squared has the higher power than the 3x, right? Of course it is. And that only the term that matter. However, when we multiply it out, notice that when we do this calculation, at the end, the x squared and the x squared cancel out. So if we don't have the 3x, that is a big problem, right? Because the answer here end up being 3x. So if we happen to drop the 3x from the beginning, here's a big trouble, big problem. Because we don't have anything left on the top. This case we have the 3x on the top. Now, of course, here we can take the derivative of the top and the bottom. But before that, make sure that it is in the indeterminate form. So put infinity on the top for x, infinity at the bottom. Right. And then you say, what happened inside the square root? That could be 0, because infinity minus infinity could be anything. Of course, that higher power. But notice that this is the square root, right? Square root cannot be negative. So unless this is undefined, unless inside is negative infinity, unless inside is negative, we have a problem. Because negative inside square root is imaginary. If inside is not negative, then that's going to be positive. Or at least 0, because square root cannot be negative. So pretty much we have infinity on the top, infinity at the bottom. And then that gives us the Habitual Rule. Derivative of 3x is 3, derivative of x is 1. So that's easy part. X squared minus square root of x squared minus 3x. I will rewrite as x squared minus 3x to the 1/2. And I take the derivative of that. Will be 1/2 times this to the negative 1/2. And then inside derivative of that. Right. Of course I put x squared minus 3x in that. 1. Now, power negative 1/2, I can move to the bottom. So I have 2x squared minus 3x to the 1/2. On the top, the derivative of this is 2x. Which of course cancel out the 2. Right? Now, what is the limit of x over x squared minus 3x to the 1/2? Now, we have x over x squared minus 3x to the 1/2. Now, unlike this, where we subtract, something might cancel out. This one, we can just take the limit and ignore that, because x squared has the higher power when x goes to infinity. So we just have x over x squared to the 1/2. Which of course we did this earlier. Square root of x squared. Square root of x squared is absolute values of x. When x goes to infinity, that is positive. So I have x over x, which is 1. So this go to 1. So the answer is going to be 3/2. Right. So, yeah, this of course you need to do a separate problem for that. Now, I go back to the original problem. Original problem, we have infinity minus. Let me just write that. Because this is a minus, we cannot just drop the lower power. Because when remove the x might cancel out. However, if this is a plus and this is at x go to infinity, this is not infinity minus infinity anymore. This is infinity plus infinity. Of course, that's still infinity. So if it is the plus in the middle, we can just drop this. But if it is minus, we cannot. Right. So, once again, if it's minus infinity, because both of them kind of the same power, right? Remember, if we happen to drop it, this is absolute value of x, which turn out to be either x or negative x, because x go to infinity, this is going to be just x. So this is as x go to infinity, we can write like that. So here we have x minus x, which is infinity minus infinity. So that's why it did not work. If it is infinity minus infinity, it is indeterminate form. If it is a plus, it is not indeterminate form. Having said that, if this is a plus, don't have to go through all of the problem. Or here, we just say, I will take the highest power of x squared minus 3x. And we just end up with that. Now since x goes to infinity, just have x plus absolute values of x, and x is positive. So we have limit of x go to infinity, 3x. X go to infinity, so it's positive. So we have 3x over 2x, cancel out 3/2. We don't have to go through all of the problem. I just want to emphasize that when it is minus, originally it is infinity minus infinity indeterminate form. This infinity plus infinity is not indeterminate form. So that's why we don't even need to go through all of the problem. Just write equal to. equal to that. Doing here, I just want to show that it also works if we use the Habitual Rule. Right, so, moving on, more examples. Let's try to find the limit of this. So, as always, the first thing we do was put in the numbers, see what happened. This is sine square, so I'm going to put sine of 3 times 0. The square there is actually, we go outside. And sine of 0 is 0. So bottom line is it is indeterminate. So we will use the Habitual Rule. Sine square. Let's just rewrite the sine square of 3x. This should be written as sine of 3x square. I will take the derivative in this form. Take down the 2 times the bracket, the derivative of the bracket. The derivative of x squared 2x. Right, inside the bracket we have sine of 3x. Sine of 3x. Right, sine of 3x. Derivative of sine 3x, it still is a chain rule. Derivative of sine is cosine of something times that something. Derivative of that. So we have 3x and then 3x. Derivative of 3x, which is 3. Yeah, because when we get used to it, just that cosine 3x times 3 immediately. Cosine 3x times 3 over 2 times x. Right. 2 and 2 cancel out. There's a 3 I put in front. Now we put in 0 again. Now, if we have to use that, of course, we take derivative one more time. The Orbital Rule certainly works. But I run out of space, and of course there will be a better way to do this. My point is, the Hablo Rule is just a tool. Sometimes it helps us to do the problem. Sometimes if we just stick to the fundamental that we have earlier in chapter 2 and chapter 3, it will be a lot easier to do. Case in point. Now, remember we have sine of x over x when x equal to 0 is equal to 1, right? Now I have the sine of 3x. If I have the 3x here, multiply by 3 at the bottom, I have to do multiply by 3 on the top to keep things balanced. Right? So why do I do that? Because when we do that, as x equal to 0, sine of something over the same thing is equal to 1. So we just have 3 times 3 and cosine of 3x times 1, right? So, yeah, don't over-rely on the Hablo Rule. If here we take the Hablo Rule, that is a product rule, which of course still work, but that will be a lot of work. My point is, we should use all the tools that we know and don't over rely on the Habitual Rule. The Habitual Rule is nice, but it has to be in indeterminate form. And even though when it is in the indeterminate form, there might be a better way instead of the Habitual Rule. And this case show that if we can just make sign of something over the same thing when x go to 0, go to 1, then we just have left with 9 cosine of 3x. Then if we put in 0, cosine of 0 is 1, so this is equal to 9. A lot better than that. Talking about a lot better, we can even do this one without any the Habitual Rule, any derivative. Notice that if I write this form again, I can put both of them inside the square. By that I mean if we can take that into the next level, meaning we put the limit inside the square as well. Sine of 3x. Yeah. So that is the square. Limit of the square is the square of the limits. If the limit exists, and then because we do the same thing, multiply by 3 top and bottom, and this go to 1. So we just have 3 times 1 square, and that is 3 square. Yeah, so it's even better. My point is, the Habitual Rule is one way to do the problem, but not the only way. Sometimes it works better. We don't even need to use the Habitual Rule. But when something like this, if we try to prove using the Habitual Rule, is extremely convenient. Don't have to do much. Don't have to do any geometry or trigonometry or quotient rule. I mean, squeeze here. Yeah. So, Habitual Rule is nice and all. It's very easy to use. Derivative at the top divided by derivative at the bottom, but it has to be in indeterminate form. It has to have a ratio of 2 functions in order to do that. Derivative at the top divided by derivative at the bottom. That's what the Habitual Rule is about. And with something like this, of course, we can use the Habitual Rule to infinity over infinity. But the way to do this is, as x goes to infinity, only the one with the highest power matters. Whether that goes to infinity or negative infinity, only the one with the highest power matters, meaning that this one has the high power, not the ax. So once again, as x goes to plus or minus infinity, only highest power term matters, not the leading term. So we cancel on x square and then put negative infinity in. So, and this equal to 0 because we have finite over infinity is 0. Yeah, a finite amount divided by infinitely many parts. Of course, that's going to be 0, too small, smaller, and eventually it goes to 0. Right. So this just shows that the Hablo Rule is nice, but if there's a better way to do that, do that. The Hablo Rule is just offer a tool to do some certain type problem, and yeah. So yeah, once again, the Orbital Rule is nice and all, but there's a little details of here and there. It's not the quotient rule, and only use the Orbital Rule for indeterminate forms. If it is not, don't do it. And the Orbital Rule requires that we have a quotient. So try to turn that into a ratio of two functions so we can use the Orbital Rule. And if there's a better way to do that without the limit, without the derivative, without the quotient rule, I keep saying that. And if there's a way to do that without the Orbital Rule, without any derivative, of course we can do that. Like this problem. Or like that problem. Right, so I stop the section here. As always, thank you for watching. See you in another video in Calculus 1.